As we do these review assignments, it's really important that you check to make sure that you know all of your formulas so you're not wasting your quiz or test time trying to reproduce formulas. So we're finding derivatives here. The derivative of arctangent is 1 over 1 plus our u squared. So we want to square this 2x times the chain rule on the 2x. So you could immediately write this as 2 over 1 plus 4x squared. As opposed to the derivative of tangent itself, here we've got a chain rule, so we've got to do the derivative of tangent first, is secant squared. Leave the glob alone. Chain rule on that inner glob. So again, if you're thinking one step ahead, you can always write your answers. You can move that chain rule to the front immediately. Our derivative of secant of x squared, here the 2 only applies to the x, not to the secant. So our outer function would be secant, so that would be my first step. And then the derivative of the inner function would be our chain rule. So the derivative of secant is secant of the same glob times tangent of the same glob times the chain rule. So we can put that 2x out in front. And again, feel free to write these all in one step if you're thinking one step ahead. All right, cosine of x over 2. Remember, this is the same as thinking of this as 1/2 of x. So our derivative of our inner glob would be that coefficient. So the derivative of cosine is negative sine of the same value times the derivative of our argument, and that would be the 1/2. So each time here there's just a little bit to rewrite. The derivative of arc cosine, and this one takes a little bit of extra work here. Remember, it's 1 over the square root, negative cosine, negative 1 over the square root of 1 minus our argument or glob squared times the chain rule on our glob, so that's our 1/2 again. And remember that here we can do some simplifying, because if we get a common denominator here by writing that 1 as 4 over 4, so this is one where we do expect you to do some simplifying. And remember what we thought of here, factoring 1/4 out of that square root. And of course the square root of 1/4 is 1/2, and I wrote this 1/2 wrong. This is really a 2 in the denominator, so that 2 right there, sorry, that 2 I should have written as a 2 here. 2 times and the square root of 1/4 is 1/2, so those two terms cancel each other out. So we've seen that before. Let me squeeze in here what we have as our final answer then. So there's an example of one that you do have to remember. Anytime you have a complex fraction, you should always get rid of that somehow or other using some algebra. All right, so our coefficient of 7 can come out of the derivative, and then our derivative of e to a glob is e to the glob. But don't forget the chain rule on the glob. So here we come up with 49e to the 7x. Our derivative of 7 to the e, notice there's no variable there. This is a constant, so our derivative is 0. And our derivative of, this is our rule of the derivative of a to the x, a constant to the x power. So our derivative is 7 to that function times the natural log of 7, and then we multiply by the chain rule on that exponent of 7. So doesn't matter what order you write this in really, but we would probably move that 7 out in front. A lot of 7s there. The derivative of a natural log is 1 over the glob, whoops, 1 over, yeah, that's right, sorry, 1 over the glob times the chain rule on the glob. So the 7s are going to cancel there, so we'll come up with a 1 over x. The log in base 7, a little bit different. 1 over the glob times the natural log of the base, and then again times the chain rule of our argument 7. So our 7s would cancel here, and we'll have 1 over x ln of 7. And here, this is the one time when we absolutely must do logarithmic differentiation. When we have x to the x, we have a variable in the base and a variable in the exponent. And the reason we need to take natural logs of both sides is that's the only way to get that exponent of x to come down out of that denominator. So we take the natural log of both sides and we rewrite the power of the log, and then we can do implicit differentiation. So differentiate with respect to x. So the derivative of natural log would be 1 over y times the chain rule on the y, dy dx. And over here we've got a product rule. So we're going to have the first term times the derivative of the natural log plus the natural log times the derivative of the x. So our first term is x and our second term is natural log of x. So that's where we're coming up with these values. Here's our uv prime plus our vu prime. So we can cancel those two x's, and we can solve for dy dx by multiplying the x to the other side. So maybe you might want to see this in a single step here. First, natural log of x. That's what's left. And now this was 1 over y. So now I can multiply both sides by y, and you might be able to write that completely as a function of x if you go back to your original. Remember that y can be written in terms of x. So if it's possible to write your derivative in terms of only the variable x, there's a bit of an advantage to that. All right, how about x to the e? Well, that's no different. Think of what you would do if that were x to the third power. So our variable is the base and our exponent is a constant. So this is a power rule question. So we bring down the exponent and we subtract 1 from the exponent. All right, some multiple choice questions. So we have an implicit differentiation problem here. So we're going to take the product rule on the first term. We'll think of this as a u and a v. So we'll have the first term times the derivative of the second term requires a dy dx, or you might use y prime, plus our second term y to the fourth times derivative of the first term. And then our derivative of this -5 would be a 0. You don't have to write that. And on the other side, our derivative of the x cubed term, our derivative of the x squared term, and the derivative of y is 1 with a chain rule on the y. So there's another y prime. So we've got two terms. We've got two terms that have a y prime in them. So depending on which side you want to move terms to here. So if I keep this first term, rearrange it maybe a little bit here, that has a y prime, and then we're going to move a y prime from the other side, and we're going to move that term to the right side. So I guess we want to subtract it, 3x squared y to the fourth. And then if we factor the y prime out of these two terms, and you don't have to show all of these steps, there's our factoring. And then we divide There's our formula for our derivative. And now that doesn't appear as our answer because we're not finished with the question yet. Go back to the question. We want to find the equation of the normal line at this point. So all we've done so far is found a formula for our slope. So now we want to find out what is y prime at the point 2, -1. So we want to plug in some arithmetic here. We want to put a 2 in for x. So we'll have a 12 minus a 4 and a 2 in for x and a -1 in for y. So that would be a -12. And in the denominator, 2 in for the x, -1 in for the y. So we would have 4 times 8 times -1 minus 1 as our denominator. So check my arithmetic here, but I think that that will be correct. So, of course, 2 negatives will become positive. That's the slope of our tangent line. But now we want a normal line. So the equation of the normal would be y plus 1 is equal to the opposite reciprocal of our slope of the tangent, x minus 2. And then all of our equations are given in a standard form. So we would have to do a little bit more. Multiply everything by 4 if you want to get rid of the denominator. And then we'd just have the -33 left. So then we could distribute that. And with any luck, when we write this in the form that matches what's given, I hope that that is choice A. And I think that is right. I already have seen the answers, so I was hoping it came out to be A. All right. In 14, we are looking for a second derivative. So let's do implicit differentiation with respect to x. So we have to remember to do a dy dx or a y prime as our chain rule. And we can solve for dy dx. Be a -4x to the third over 4y to the third. So those 4's can be gone. And now we do the second derivative with respect to x. So we need a quotient rule, low, d high minus high, d low. That's where our chain rule comes in, dy dx over y to the 6th. And our dy dx is our first substitution. We're going to replace that with our previous answer. And when we do, I'm going to just reorganize these variables. When we replace that, maybe I don't want to jump the gun here. You can do the canceling right away, but I should show you the steps here so we don't lose anyone along the way as you're watching the video. So here we did some canceling. Y squared cancels, so we still have a y. So we still have to multiply to get rid of this y that's left over. And we have to remember to distribute that so it becomes a y to the 4th in the first term. And now we have a negative times a negative. So these all look very familiar, similar problems to what we've been doing in previous assignments. And now we are hoping when we factor the GCF of 3x squared that we will notice our original function. So we need the second substitution should be right here. So x to the 4th plus y to the 4th was indeed our original equation. That is equal to 1. So we are left with a second derivative of the opposite of 3x squared over y to the 7th. And that is our choice E. All right, in number 15, we want to find the derivative first, and then we want to find the numeric derivative specifically at 1. So the derivative of arctangent is 1 over 1 plus the glob squared times the chain rule on the glob. So that would be a 2x. Now, you could clean this up if you distribute that binomial squared, and then you'll have a 1 plus a 1 term. Or you can say, well, I'm going to only be interested here in what happens when x is 1, so why don't I just go ahead and substitute that and then clean it up. So instead of cleaning up your algebra, you could do your arithmetic substitution and then just come up with your answer. So it looks like we have a numerator of 2 and a denominator of 2. Let me try that again. I don't think that's right for our denominator. I think this value is 2, and then we still have to square it. So how about 1 plus 4? How about 5 as our denominator? So 2/5 is the same as 4/10 to see what we have as our multiple choice format. So it looks like we've got letter E. And we're doing, again, a numeric derivative. So we're doing the derivative of sine x to the x. So again, this is the one case where we must use logarithmic differentiation, when we have a variable in the base and a variable in the exponent. So once we take the natural log of each side, then that exponent can come down in front. So remember here that we'll have some chain rules. It's very important to watch carefully now. So now we're ready for our implicit differentiation with respect to x. So the derivative of natural log of a glob is 1 over a glob times the chain rule on the glob. And on this side, we've got a product rule here. This is our u and our v. So we'd have the first term, u, times the derivative of that natural log glob would be 1 over the argument times the chain rule on the argument. So that's only our uv prime. So now we still have to add our v u prime. So our derivative of x is just 1. All right, so what do we have here? Let's just rewrite that. Right side here, x cosine of x over sine x. Now you could write that as x cotangent of x if you prefer, whatever you're better at. And then we've got to add the natural log of the sine of x. And then our dy dx, if we clean this up, we want to multiply this y to the other side. And instead of writing it as y, instead of writing this as y on this side, can we replace it with what y is equal to? Sine of x to the x. So this all looks like a little bit of a mess, but now remember what we're going to do. We're going to plug a specific value in for our x value. So now we want to find f prime, in other words, find the slope or the dy dx at pi over 2. So unit circle, pi over 2. Our cosine is 0 and our sine is 1. So this will simplify nicely. So we're letting x equal pi over 2. We could write it with, I should keep you used to doing this, dy dx such that x is equal to pi over 2. Good notation for your readers. So the sine of pi over 2 is 1 to the x power. And of course 1 to any power is still going to be 1. So you don't need to write that. And then we have our pi over 2. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. The sine of pi over 2 is 1, so we have the natural log of 1. So we're getting there. So 1 to any power is still 1, and this first term is 0, and what's the natural log of 1? So e to what power produces 1? That would be a 0 also. So does it look like we come up with 0? And let's find our choice in our multiple choice. So we're going to choose A. So a lot of work just to get a 0. 17. So rectilinear means straight line motion. Rectilinear, you're stuck on a straight line highway. So our particle has a position function s. T is measured in seconds, and s this time is measured in meters. Find the total distance traveled over the interval from 1 second to 3 seconds. So we need to know if this particle is ever going to turn around. So we better find out its velocity function, 6t to the second minus 18t plus 12. So it can only turn around. It might turn around if its velocity hits 0. So we'll factor. That should be a 3. So again, if it's in a non-calculator section, it will be easily factorable. So our critical numbers, when the velocity is equal to 0 at 1 and 2, they are both single roots, so we expect it to change directions. Now, we're only interested in the interval from 1 to 3, so what we need to do here, if we think of our intervals, on the interval from 1 to 2, look at your velocity function in factored form right here. If we put in a number like 1.5, we can see that we have 6 times a negative times a positive. So the velocity is negative. And then on the interval from 2 to 3, if you pick a number like 2.5 for time, then all of the factors are positive. So first we know that the object is moving left. And then we know that the object is moving right. So for the total time, you have to be careful to not just take its starting position minus its ending position. That would be the net distance. So for total distance, you have to be a little bit more careful. So we have to find the position at critical numbers and at endpoints of your closed interval. So we have to find out, where did it start at time 1, where was it at time 2 when it turns around, and where is it at time 3. And then we can add up our total distance. So we want to take our position function now, and we want to put 1 in for the time value. And we should come up with 5 meters. And then you can do the substitution here. I'm just going to continue. You can pause the video to do some calculations. At 2, I have 4 meters. And at t equals 3, I have 9 meters for its position. So total distance traveled. First it went backward 1 meter, and then it went forward 5 meters. So I think our total distance traveled should be 6 meters. Now, for multiple choice questions, you don't have to show your work as neatly as this, justifying it, but that's helpful to explain your work here as I'm doing the video. So 6 meters total. All right, so notice, by the way, that our net distance, it started at 5 meters and ended at 9 meters. So our net distance would have been only 4 meters. And that usually would show up as one of the distractors. I'm surprised that it doesn't. All right, in number 18, we want to do a linear approximation of this function. And we want to find out, we want to use our tangent. So we want to use x1 of 1, and you can see why. I hope if we put 1 in for x, we'd have the square root of 25. So that's our easy point of tangency. All right, so we got to do a couple of things. We've got to find the equation of our tangent line. So f prime, this is this glob to the 1/2 power. So we can do the power rule to the negative 1/2. And then we would do a chain rule if there was one, but the chain rule would, of course, just be 1. So there's our derivative, and we want to find the derivative when x is equal to 1. So you could write it this way if you wish. When x is equal to 1, let me put it in there. So we would have 1/10 as our slope, and when f is equal to 1, notice our y coordinate is 5. So our tangent line would be y minus 5 is equal to 1/10 x minus 1. And now we want to use that tangent line to approximate 24.98. Well, look carefully at your function. So to be the square root of 24.98, what would x have to be? So now we're going to let x be equal to 0.98. Okay? So if x is equal to 0.98 instead of 1, then this would be the square root of 24.98. So we're going to substitute the specific value nearby where x is equal to, 0.98. So we'll have y minus 5 is equal to 1/10. You could write that as a decimal if you wish. And when we put 0.98 in here, we'll have a negative 0.02, or if you prefer, negative 2/100ths. So whether you like fractions or decimals, your choice here. So we would have negative 2/1000ths. And when we add 5 to each side, now we have to be a little careful here. So if we want to change this back to decimal, for example, 4.998, if we're subtracting 2/1000ths. So this is our approximation. So we were approximating the square root of 24.98, and we came up with an approximation that seems quite reasonable, and it is our choice F. All right. Oh, I guess I said that too soon. I better read. That's a 0.988. We wanted 4.998. How about G? That looks better. All right. Proceeding. Sorry, this is getting to be a long explanation here. Another linear approximation. So our f of x, if I think of f of x here as 2 plus x to the negative 3 power, then our f prime of x would be negative 3, 2 plus x to the negative 4th power. And we want to use the specific value. Here they show you as a constant. We want to let this be specifically at 0. So let's put 0 into our variable here. So if x becomes 0, we'll have this value. So this would be a negative 3 over 16 as our slope. And our point of tangency, we want to put 0 in for x into our original function. So when x is 0, it would look like 1/8. So our tangent line, here would be y minus 1/8 is equal to our slope times x minus 0. And we want to, the form up here is really just coming up with this value. So if I would move the 1/8 to this side. So these answers in multiple choice form might have been a bit confusing. but this is our evaluation here, so it's turned around, but that is letter E. So that one was given in a little bit different format. All right, find a limit. Well, we haven't done this practice for a while, so here's our limit laws. And these are our theorems. We would like to make this look like those two special theorems. Our theorem about the limit of cosine of x minus 1 should just be over x. So the trick here is that we would need to bring that 1/2 out of that part. And the problem with our second, when we split this up using our limit laws, we can do the limit of a difference is the, and I think, by the way, that should have parentheses around it. And that maybe was the trick. Maybe they didn't. I took this from another book. Maybe they didn't actually want it to be two limits. Well, let's find out. Sine of x, we want this to just be an x here, so we need to bring that 1/2 out as well. So this part, this limit becomes 0, and this limit becomes 1. So we have 0 minus 1/2. So I think we're going to go with E. So I think this was badly written, parentheses around there. All right, and here's our question about linear approximations. And remember that any time that a graph is concave up, the tangent line will be below the graph. So this is concave up increasing. What would concave up decreasing look like? It would look like this. But our tangent lines would still be below the graph. And what does concave down look like? Concave down decreasing. Concave down decreasing. And concave down increasing. So it really doesn't matter whether it's decreasing or increasing. Don't be fooled by that. When it's concave down, the tangent lines will be over estimates. And when it's concave up, the tangent lines will be under estimates. So concave down, we have over estimates. Concave up, we have under estimates.